Welcome back to section 2 of chapter 4. And this is the second part of what we were looking at last time, which is what derivatives tell us. Last time we had an equation, and we would take the derivative and second derivative to find the extreme values, maximums, minimums, points of inflection, intervals of increasing, decreasing, intervals of concave up, concave down. In this section, we're not going to get the equation. We're going to get information about the derivative and second derivative, either in a table form or in a graph form. And we're going to find some of the same things that we did yesterday. So in this case, there's less math that we're doing. It's more observation and thinking. And we already know what these things mean, so we're going to jump straight into some problems. I know, stop being sad. Anyway, so the first one, we have a table. We have a function f is continuous on the closed interval, and that f of negative 3 equals 4, f of 3 equals 1. So it's giving us the endpoints here. The function f is twice differentiable, except at x equals negative 1, and we can see at x equals negative 1, the derivative does fail to exist. That's okay. All that means is that the slope changes very suddenly there. So we have a cusp. Because it's continuous, so it's not going to go to infinity or anything. It's just a cusp. And then the functions f prime and f double prime have properties as given in the table below. So it gives us intervals in which the derivative is positive, negative, and 0 or doesn't exist. So those would be our critical points, would be x equals negative 1 and x equals 1. So those would be our critical points. And then we'll get to a question. What are the x-coordinates of all absolute extrema of f on the interval? Justify your answer. So we need absolute extrema. Now we can't just plug it into the function like we did yesterday because we don't have a function. So we do have to use more thinking. Sometimes it's not possible to find the absolute extrema, but for most of the ones that we'll be looking at, we can. So if we look at the function, we're starting at an endpoint, and we're going positive, and then we fail to exist, so there would be a cusp, and then we're going negative, 0, negative. Well, absolute extrema. Should make sense that this area would be the absolute maximum, because we're going positive to get to that, and then negative all the way down to the end of the interval. So that would be the highest point in the interval. So we have a max at x equals negative 1. We can't find out what that maximum is. We just want to know, where is it? What are the x coordinates? And now minimum, the way I drew the little graph here, it looks like the minimum is down here, but that's not necessarily the case. How could we find out where the minimum actually is? Well, by what we're looking at, it's going to be one of our two endpoints, because from the maximum, we'd be going down all the way to the end of the interval in either direction. So the minimum was going to have to be one of the endpoints. How do we tell which one it is? They give us the endpoint values. Which one's smaller? F of 3 equals 1. So it is in fact this one over here on the end. But that it did not have to be. So we have a minimum at x equals 3. So we just found the absolute extrema. Justifying your answer would be writing down some of that thought process. The only maximum, or we're going up to get to it and then down all the way to the end. So x equals -1 has to be where the maximum's at. And then the minimum, in this case, has to be at an endpoint because we're going down to get to each endpoint. And f of 3 is the lower of the two endpoints. We'll also be looking for the x-coordinates for the points of inflection. So the points of inflection, let me get rid of some of this. The points of inflection are where the second derivative equals, or not where it equals 0, where the second derivative changes sign. So on this first one where it fails to exist, it's positive. It doesn't change signs. On the second one, where it's 0, it's going from positive to negative. So we have a point of inflection at x equals 1. And that's really all that is. Like, it's not going to be an endpoint or anything like that. All right, and then next, and the last problem we'll be doing with this one is sketch a graph. Sketching a graph can be fun. I enjoy it. So sketch a graph that satisfies the given properties of f. The very first thing I would do in sketching a graph is put in your endpoints. We know the endpoints. Those are distinct points. It's always nice to have starting points. If you don't have distinct endpoints, you just have to make something up for where they might be. But if you have distinct endpoints, put those in. Start with those. And then the second thing I would do is I would put faint dotted lines at those critical points. I do that just so that I have kind of some guidance when I'm drawing. Like, that's where I know I'm going to have to do something. Either have a cusp, or I'm going to have maximum or minimum, or something like that. So it just gives me something to aim for. And now we can look at each section individually. You can graph it using the derivative, and then go back and change things and make it work for the second derivative. This one's all right. We can actually do section by section. So this first section, going to a cusp, so we have a cusp at x equals -1, we're going to have a positive derivative, which means the slope's going to be positive, and we're going to have a positive second derivative, which means it's going to be concave up. So coming from our starting point, we're going to have positive derivative and concave up. And then the next one, it's going to be negative, still with the positive derivative. And we're going down towards a slope of 0 at the end, at an inflection point. So it's coming down to a slope of 0, and then the slope is still going to be negative going down to the end, and it's going to be concave down. So from there, it can go like that. So that's one thing this graph could look like. Yes, it could look like different things, but that's one way it could look. And we just did it using the slopes and the concavity. We're able to sketch a graph of what the function might look like. Now, what is this maximum here? Impossible to tell. Like, we don't know. It's right there for now. And so it could be up a lot higher, it could be down a lot lower. There's lots of things that this could happen based on your drawing. But this is a graph that satisfies the given properties of f. So if to the next type of problem, in this case, we're not given a table, we're given a graph. Notice this is the graph of the derivative, not the graph of the function, which means when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. Getting your mind around the y value to slope, just going back and forth, it is something that does take a bit of work. So, what are we going to do with this type of problem? For what values of x does x have a relative maximum and a relative minimum? So a maximum is when the derivative goes from positive to negative. In this case, it's going from positive to negative. We have a maximum at -2. And there's no other time when it's going from positive to negative. This one over here, it's positive, but then it stays positive. If we were graphing that, that would look like one of those things. So that's the only maximum. Then we have a minimum when x is going from, or when the derivative is going from negative to positive. Like right there, it's going from negative to positive. That will be a minimum of the functions. That'll be at x equals 0. And so those would be our maximum minimum. This one only has one of each. And then for what values of f is the graph concave up? Well, the second derivative will be the slope of the derivative, so it's concave up when the derivative has a positive slope. Concave up on from -1 to +1. You could go -1 is less than x is less than +1, or -1, comma, +1, in parentheses, not brackets, parentheses. And so it's from -1 to +1, and then also from 2 to 3. And 2 is less than x is less than 3. And 2, comma 3. And there we go. We could actually graph this. This question doesn't actually ask for it, but we could look at the graph of the function as well, because we can tell when we have maximums and minimums. Like we have a minimum here at 0 and a maximum at 2. So we know it'll be going up to hit a maximum, down to hit a minimum, up to go like that. So this is something like what the function could look like. It is possible you could graph these, but we don't know. We don't have any clue as to whether it's all above the graph, below the graph, like what's happening with y values. So we probably won't be graphing on much today, but that is something that at some point this year you'll be doing, and you actually have the skills to do it now. So that's it. That's all we're doing today. Looking at tables and looking at graphs and then telling stuff about the functions. So keep working problems, keep asking questions, and as always, happy mathing.